So if we know that potential difference is what pushes current down a wire, well then what is it that impedes current? What slows it down and makes it hard for current to flow? And that is resistance. So resistance is what's impeding current and stopping just sort of infinite current flowing down your wire. You've got this potential difference that you set up from your battery or from plugging in your device to the wall that wants to push current down the wire, but the wire maybe is very thin or maybe it's not made of superconducting material. Then that will resist how much current can be pushed through, and that's what resistance is. Symbol for resistance is pretty straightforward. It's a capital R, and the units are ohms. And an ohm is a Greek letter. It's a capital omega, and it looks like that. So that is a unit of ohms. All right, so what is resistance really? Well, it's like the friction that impedes or slows down the flow of current through some part of your circuit. A nice analogy might be maybe rocks in your river, right? If current is how much water is flowing past a certain point per second, voltage is the height difference, maybe from just sort of a gradual rapids like this, or maybe a waterfall. That height difference is what pushes the current, but what slows it down is maybe the narrowness of the river, or all these rocks in there kind of pushing against the current. So you can think about that as a nice analogy maybe for resistance. All right, so here is a very, very simple circuit. So this symbol right here, this is a symbol for a battery. So maybe you have a 9-volt battery. And then this is a wire that connects right back to the battery again. We want to think about how much current will be drawn into this battery. So don't do this at home. But if you had a battery and you took a wire and you just connected one end of the wire to one end of the battery and then the other end of the wire to the other end of the battery, what would happen? Well, in this sort of situation, you have nothing resisting you, right? This wire, if you use a nice, good conducting wire, then that wire has a very low resistance to it. So there's just not much pushing back, and there's something pushing forward. It's not huge, but 9 volts is still something. So 9 volts is trying to push on that current. Not much is slowing the current down. And so what you get is what's called a short circuit. A nearly infinite amount of current is drawn out of the battery. So if you have a battery pushing on the current, trying to make current flow and nothing slowing it down, no resistors anywhere, then you're going to push infinite current. In reality, the wire itself has a little bit of resistance, right? So it won't be quite infinite, but it'll be a lot of current. And that's a short circuit. You don't ever want to do that. Pulling an infinite amount of current out of your battery is really hard on your battery, and it will heat up a lot and could actually light on fire. It can be very dangerous. So don't ever do that. Don't short circuit your batteries. It's really not a good idea. It's not safe at all because you'll be pulling way too much current out of those batteries. So how do you actually figure out resistance? There is a little bit of resistance in every wire, and it's based on a few things that kind of make sense. So the first thing that will impact your resistance of a wire or any sort of device is the resistivity of the material. So resistivity is a property of the material, and that's this little, it looks like a P here, but it's not. It's actually the Greek letter rho. So this is a rho. It's resistivity, which is the property of a material that tells you how much of an insulator or how much of a conductor it is. So in grade 9, you probably learned that things are either insulators or conductors. In reality, everything kind of falls on a scale there. Some things are really great conductors. That means that they have a really low resistivity, whereas other things are more towards the insulator scale, and so that side is going to have a higher resistivity. And everything kind of falls on a scale in there. The units of resistivity are ohm, meters. This is what you'll see for the SI units there. And it kind of makes sense. So a higher resistivity, that means like a more insulating thing and more insulating material, it's going to lead to a higher resistance. Also on top is the length of the wire. So L is the length of the wire. So of course, it's the length that has units of meters. So this kind of makes sense too, that it's on top, right? So a higher length is going to lead to a larger resistance, right? If you have a longer wire, that's just more friction, more stuff to bump into for the current. So it's harder for the current to go down. So the longer wire that you have, the more resistance you're going to face. On the bottom here is what's called the cross-sectional area of the wire. So cross-sectional area of the wire. So what I mean by that is if this is your wire here, we know the length of it, right? That's L. But if I kind of zoom in on it, it's probably a cylinder. The area, the cross-sectional area is this area right here. So that is the cross-sectional area. Most of the time, that cross-sectional area is usually going to be a circle. So it's usually going to be pi times the radius of the wire. So that right there is the radius of the wire squared, right? So it's usually a circle. So that's for a cylindrical wire, which is most wires, right? You don't see too many square wires out there. It's an area, so it has units of meters squared, just like you'd expect for an area. All right, so how does resistance impede current exactly? Well, if I think about it, voltage is going to increase the current. So I would put voltage on the top, or potential difference increases how much current flows down your wire. If you have a higher waterfall, more current of water can flow. You have more something pushing this current down the wire, so more current will flow. And resistance impedes current, so we're going to put it on the bottom. So R is going to slow the current down. So we're going to be dividing by R. This is actually a really famous law. It's called Ohm's Law, but it's not usually rearranged this way. Usually it's rearranged by multiplying both sides by R. I'm getting something like this. The potential difference is the current times the resistance. And that's the most usual way to write out Ohm's Law, which is probably the most important law in this whole unit. Really handy one and a pretty famous law in electricity. So the potential difference is the current multiplied by the resistance of any aspect of your circuit. This is true in the circuit as a whole, but also true in all of the little details of your circuits. Let's try a little example problem. So let's say you have a 9-volt battery. So my potential difference is 9 volts. So I'll just write my given down here. And I have this pencil here, which is 15 centimeters long. The length of my pencil, and the pencil is essentially going to be a resistor here, is 0.15 meters. We'll convert that into SI units right away. We complete the circuit using a copper wire, and copper is a really nice low resistivity kind of thing. So copper wire, we'll just assume it has like no resistance. So the only resistor in this circuit is going to be the pencil. The graphite itself has a resistivity. So resistivity, the symbol is rho. So remember, that's not a P, it's a rho. Just to note the difference, a P has a stick, a rho does not have the funny stick up here. There's no stick like that for a rho. A rho is just like the curly kind of P, like that. So resistivity is rho, and the resistivity of our pencil, or the graphite inside our pencil, is 6 times 10 to the negative 5 ohm meters. It's already in the right units, that's good. We know the diameter of our graphite, so that diameter is 0.7 millimeters. Let's convert that right away to meters, so times 10 to the negative 3 meters. We're trying to solve for I. All right, it seems like a good idea to probably start by just getting the resistance. So let's use our new equation here for resistance. Resistance is the resistivity, so the property of the graphite, times the length of that graphite pencil, divided by the cross-sectional area. And the graphite inside your pencil is very much like a wire. It's a circle, right? A cross-sectional area is a circle, or the graphite itself forms a cylinder. So pi, oops, forgot the R. Pi r squared is the cross-sectional area. So this area here is going to be pi r squared. That's the cross-sectional area of a circle. So we can sneak that in. That tells us a nice little equation here for resistance. And we know rho, we know L, we know the radius, or at least we can get it. It's just going to be half of the diameter, right? So R If D is 0.7, R is going to be 0.35. Don't forget to keep it in SI units though, so we'll need that little times 10 to the negative 3 to replace the millimeters. All right, so that gives us R. A big R is in resistance. I want to know the current, and so I use my nice Ohm's Law. Potential difference is I times R. Rearranging this for I, divide both sides by R. And that gives you current will be delta V over R. So our next move is just going to replace the R on the bottom here with what we know it is, which is this whole equation here. So we're going to take all that and sneak it in for the R on the bottom. So rho L over pi R squared. What that gives me though is something kind of ugly, right? It's like a fraction over a fraction. That's not very nice. It would look prettier if I do this. So if I'll write the delta V first on top, and then I'm going to multiply by the reciprocal of this fraction. So that puts a pi R squared on top and puts the rho L on the bottom. And so that gives us our nice equation for current. So you can plug all your numbers in now. Delta V is 9. There's a pi. The R squared, so that's your radius squared. That's the point. Oh dear, I'm totally going to run out of space here. I'm going to erase some stuff to give myself a little more room. So, I think I'll erase a little more actually. Okay. So we've got delta V is 9, pi. R squared is 0.35 times 10 to the negative 3. It's being squared. And then rho L, so resistivity, is 6 times 10 to the negative 5. And the length is 0.15. So we want to toss all those numbers into our calculator. So 9 times pi times 0.35 times 10 to the negative 3 squared divided by 6 times 10 to the negative 5 and divided by the 0.15 as well. And what we get is a current of 0.38 amps. And that is the current that would flow through that wire.